introduce apprenticeship learning via inverse reinforcement learning. Apprenticeship learning uses inverse reinforcement learning to find the reward function for the optimal policy through the expert demonstrations. Once we have a reward function, then we can use reinforcement learning to find the optimal policy for the reinforcement learning agent. Let's see a Markov decision process without the reward function R. We have actual D is the initial state distribution. According to the definition of the expected state value function, or agent at a state S, the expected state value function is equal to the expectation of future discounted cumulative reward. It means the reward along one episode. We need to calculate the expectation of all the returns along each episode. So that means this expected state value function equal to this reward, the cumulative reward. That is the future discount factor. If we assume this R is a linear function for parameters W, this phi is the basis function or is a feature mapping. That means it maps the state to a feature vector. So we have this linear relationship. Use this product of W and phi. We express this reward function R. Because this W is no relation with the time, so we can move this W outside the sum and the expectation. Because this part is no relation with the W, so we can define this as mu is a feature expectation. From the definition, we can have this relation between the expected value function and the feature expectation through this parameters W. This W connected to one side to the feature function R, and another side to the feature expectation. That means we find that R makes the policy is optimal. So for example, one expert generates a trajectory using his policy pi e. To use the inverse reinforcement learning to find the reward function, we need the feature expectation from the expert policy. However, we don't know this true value, so we use a linear function to estimate this true value. That means apprenticeship learning uses inverse reinforcement learning to find the reward function for the optimal policy from the expert demonstrations. And then we use reinforcement learning to find the optimal policy for the reinforcement learning agent. So that the feature expectation from the learned policy should be close to the feature expectation from the expert policy. The steps to find the optimal policy using the apprenticeship learning is listed here. First, we just randomly pick up a policy, and then we calculate the feature expectation from this initial policy. And then we use the inverse reinforcement learning to calculate this T as includes two terms. One is we select different policy and calculate the feature expectation and compare to the feature expectation from the expert policy, and we make this difference is minimal. And then we select the parameters W and make this value is a maximum. From here, we find this W, and then from W, we can calculate that we can get the reward function. Later, we will explain how can we from using the in reinforcement learning to find this parameters through the projection method. So once we have this t, of course, if this t is smaller than the criterion, then we terminate the iteration. And then from this W, we can find the reward R. Once we have a reward R, we can use reinforcement learning method to find the optimal policy. And then from once we learn the policy, then we can calculate his feature expectation. And then now we go next iteration step by step until reach the convergence. This is just like two steps. One is just this is just suppose this is the optimal policy. Here right now is the export policy. And then we just from this this is the policies we found previously. We select which one will have a feature expectation closer to the feature expectation from the export policy. And then we select this W, make this a maximum. That's a big steps. Once we get to the convergence, we will have this we will have this policies. Here is a projection method to calculate the coefficients W, parameters W. Here, this is the in the second step, this is T here with the constraints. This means this is the stated value function from the export policy. Here is the stated value function from the policy we learned. And here is the margin. This is just to make sure each parameter is less than 1. So to find the parameters W from the using the project method, here that's because to calculate this W, we need as a feature expectation from the export policy, and this one is from the learned policy. However, learned policy without this bar, that means this phi is the current step we found from the inverse reinforcement, and this with the bar is the previous feature expectation we found, and this is the export. This is the feature expectation from the export policy, and so on. And we to calculate the W, we need to calculate this mu with the bar. That means the first step, for example, we have randomly pick a policy pi 0, and from pi 0, this is mark 1 from this value from the export policy, and from this initial, calculate this from the initial pi to calculate the initial feature expectation. We got this W1. So from the W1, we can calculate we can get the reward function R. And then from this reward function R, we give to reinforcement learning. And also we give this value to reinforcement learning. We use reinforcement learning, we can find this pi. And then from pi, then we can calculate this feature expectation. Once we have these 3 points, And then now we can calculate the W2. It means we can update the next W2 from this point to this line. And so on, we follow the same way, calculate this one, and the same thing, from this bar to this point, mu, and we calculate the W3 and W4 until this distance, this T is smaller than criterion. We get a convergence result. For more details, please check with this reference. Thank you. Bye.